So without more introductions, because we're a little bit late, I'm going to go ahead and let Rachna start.
Thank you, Dr. Valantia. Good afternoon. My name is Rachna Tiwari, and I'm an assistant professor at the University of Tennessee at Martin. I teach a lot of the ag business, ag economics, risk management classes over there. As some of you may know, we are located in a very productive zone of the state, the western part of the state, and there's a big emphasis on this undergraduate program there. So I pretty much teach, a lot of those farm and ranch, undergrad, ag business program classes there. And I'm happy to be here today. Thank you all for being here, and the Department of Ag Resource Economics, UT Knoxville, thank you for this opportunity. I'm hoping this will be a good interactive discussion here, and we'll probably get something out of it. And please feel free to ask questions if you have any questions. So thank you. Without further ado, I'll just go and start off. So today I'm going to talk about groundwater resources in Texas High Plains. That's kind of the case study approach is where I'm coming from. But before that, we'll just talk a little bit more in general about groundwater resources in the US and the concept of water scarcity, security. Just wanted to give you all some background on that before I go really, into the case study thing that we did in Texas High Plains. All right, so I'll start with some talk on water scarcity and water security, and some perspective on the world side of it, all right? And then I'll talk about groundwater and US agriculture and how climate variability or climate change plays a role, and what are some of the changes we are seeing in the past several years. Then I'll talk a little bit more about, that's where I talk about the case study, that's what's going on in the Texas High Plains. So I went to school in Texas, I spent a considerable time there, so a lot of my research has focused in the past several years about groundwater related research and management policy related approach towards groundwater management in the Texas High Plains area. So that's what we will be talking about in the later part of the presentation. Okay, so let's talk about the world water resources first. I'm sure that several of you know that overall about 97% of the total water that's available in the world is not suitable for human consumption, right? Where does all of that water lie? It's in the oceans, it's salty, right? It's not available for human consumption. There's only about 3% of this fresh water that's actually available for any kind of use, like domestic, potable, irrigation, municipal, so many other possible uses that we could be looking at, all right? And out of the scarce 3%, about 68% of that is untapped again, because that's a lot of that water lies in the glaciers, snow-capped mountains, and that's pretty much untapped. So where do we get all of our water, fresh water supply from? The groundwater, right? That pretty much just sums up how important that is. I think that's a good way to think about it. And a little bit of that is also in the fresh water that's in the surface lakes and other surface water bodies. But pretty much about 30% of the available about 100% of the available water supply in terms of the groundwater comes from groundwater in the freshwater sources. All right, now given that a lot of this groundwater is scarce, and you all know that population is on an increase, and we are projecting about 9 billion by the year 2050, so that exerts a huge pressure on these limited resources, right? So what happens when demand exceeds supply? That's a simple question, right? Scarcity. A lot of scarcity occurs, which we are witnessing in several different areas, right? And the scarcity might vary as we move from one part of the state to the other, one part of the country to the other, one part of the world to the other part of the world. Okay, so this is highly variable, as you can see. All right, so I just wanted to, this is I think a good summation or a good description of physical and economic water scarcity in the world, and this was given by the International Water Management Institute, which is a United Nations organization, and they suggested there's about 4 different classifications of water scarcity that we can look at. Let's look at the physical water scarcity first. So what's physical water scarcity? There's kind of this semi-orange shaded region, some parts of Asia, some parts of US, significant part of US actually, towards the west. Several parts of, other parts of Asia, some parts of India. Okay, all of these areas. They are facing physical water scarcity. So physical water scarcity is where water resource development has exceeded or approached sustainable limits. That's about 75% of the water that's available in the lakes, rivers, has been exhausted, or even if it's not been exhausted, it's not able to be tapped, right? So it's not always the case that dry areas are water scarce. There might be a case that dry areas do have water, but there's not sufficient potential to be tapped, all right? So that's physical water scarcity. Then a little bit of these lighter orange shaded regions are approaching physical water scarcity regions, which are some parts of the US, you can see some parts here, and then some other portions up in East Asia, some parts in Africa. These are about 60% of the water flows are withdrawn. So these are approaching physical water scarcity in the near future. Third is, and the most important, the most crucial one, is economic water scarcity. That is probably something which we all are concerned about. And this is in significant portions of Africa, significant portions of Central East India, some other portions in South America. And economic water scarcity is when human physical capital constraints do not allow a lot of these available resources to be tapped. So a lot of financial constraints do not allow a lot of these resources to be used for meeting human, domestic, or agricultural needs. Okay? So these are kind of the major areas where all of these hunger, malnutrition problems exist, and we are facing those issues in those areas, as you can see from studies in Africa or some parts in India as well. And finally, little or no water scarcity. Okay, so according to the UN classification, it's a good news for some areas in the US, and then some areas in South America, a lot of Europe. There's little or no water scarcity. Okay, but this is kind of just a generic classification. That doesn't mean that we don't have to be concerned about it, but it's still so far there's not a lot of alarming issues that's occurring in these areas. So I think it's a good overview of the world classification of water scarcity. So if several regions in the world are experiencing water scarcity, there's a lot of concern that might arise about what is called as water security, right? So let's see what water security is. So water security is kind of a very holistic definition that the United Nations Forum on Water has given. So what they say is water security is kind of a capacity that you can think of a population to ensure that there is a sustainable access for several different facets for which water is used. Okay? So the first is there should be adequate water for drinking and human well-being. That is something it's probably on the top list. There has to be sufficient access to water for maintaining and preserving ecosystems. Then there has to be some capacity to make sure that whenever there's a water-related hazard or climate change-related issue, floods, droughts, or things like that, they do have some access or some kind of preparedness to deal with such issues, right? And finally, there has to be adequate water for economic activities and development. So if 4 of these facets are well managed in a population area or within a population area, that's kind of, you can think that that area is water secure, okay? And then some areas might be lacking in one of the several areas, but this is what they are targeting towards, okay? So now let's look at some of the current facts for the US water resources. About 80% of the nation's water withdrawals go towards power generation and irrigation. So that's a significant proportion of overall water withdrawals, okay? And that includes both surface and groundwater. About 3.9 trillion gallons of water is consumed in the US per month, okay? And then finally, 20% of the water withdrawals are from groundwater, which itself is a scarce resource. And these are average numbers for the whole nation as such, for the whole country, and definitely vary from one part of the country to the other, okay? Let's look at groundwater withdrawals for the United Nations as a whole, okay? Where would you expect the maximum groundwater withdrawals? Where there's maximum irrigated agriculture, right? The western part of this country, California, has the highest water withdrawals, as high as 20,000 to about 40,000 million gallons per day for irrigated agriculture, okay? And then there is some other highly agriculturally productive areas like Texas, Arkansas, Arizona, Florida. Some of these also do have high withdrawals. And then some relatively high withdrawals are also in the west, Oregon, Idaho, Nebraska, all of these states. And then some of the states which do not rely a lot on groundwater, probably because there's not a lot of agriculture in that area, or there's a lot of surface water resources that are available, as you would expect, is the eastern part of the country, right here, all of this. Okay? So you can see how groundwater and resources are variable across the different states in the country. Okay? Okay. Now, since my talk is also centered a little bit heavily actually on climate variability, what happens to these water resources when there are variations in climate, right? So the first thing that would come to your mind is whenever there's a fluctuation in temperature or a drought occurs or things like that, immediately impacts the surface water resources. But do they also impact the groundwater resources? They surely do, right? Why? Because there's a definite recharge that goes into the groundwater to recharge those aquifers or those groundwater bodies that do supply groundwater, right? Okay. So surface water resources become unreliable in those cases, and natural precipitation definitely becomes scarce, right? And that is something we probably saw in the 2012 drought that happened here. You know, a lot of those high production areas saw this issue that, you know, those who were heavily reliant on surface water or on natural precipitation saw some heavy decline in production during the 2012 drought. Okay, and definitely the pressure increases on groundwater resources. Now, what about semi-arid areas? So, since we are in the east side of Tennessee, and you know, Tennessee by itself is not a very dry region, but if you look at some of the most semi-arid regions in the country, there's definitely a huge pressure on the groundwater resources in those areas, right? And more so for those areas where the economies itself are heavily reliant on agriculture, right? So all of that water is pretty much coming from groundwater withdrawals, okay? So one such economy in the country, which is one of the highest productive economies in the country as well as in the world, is the Texas High Plains. Okay? And groundwater management has emerged as one of the most crucial policy areas in that region, because there's so much that groundwater impacts in those regions. Okay? So today we'll talk about this. I'll now focus a little bit more on the study that I'm going to talk about, which is the case of the Texas High Plains. It's located in this shaded region of Texas, okay, the High Plains area. I'm sure you all have heard something about it sometime, maybe while reading an article, or when you heard about Texas, you definitely heard something about it, about the high levels of irrigation that's in that area, also about the big livestock industry that's in that area, which also is dependent on groundwater, right? Okay, so let's see what we have here. So my study is basically using climate scenarios, which are nothing but future projections of temperature, precipitation, and other climatic factors, to forecast or to predict what could happen to these groundwater resources and how the impact on these groundwater resources will impact net revenue, production, cropping systems, and other economic parameters in the study region. That's what we are trying to do here. This study was funded by the Ogallala Aquifer Research Program, which is a USDA ARS program, and it's a big program there. And we also had some people from the Climate Science Center at Texas Tech and the ARS lab at Texas Tech working on crop modeling and climate science related areas who were part of this team. So it was kind of a multidisciplinary project, and I was doing the economic side of it when I was there in Texas. So, and I think very recently we should have this online. It's recently been accepted in the Journal of Water and Climate Change, so I think it should be up online in the next several months. But this is kind of the main area that we are looking at. Okay. So let's start with looking at the water use in Texas now. We did see a little bit on the groundwater use in the United States. Let's look at what's happening in Texas. As you would expect, 60% of the total water used in Texas comes from groundwater. Okay. Only 40% comes from surface water. Now, out of the 60% water, as you would expect, about 8% goes towards irrigation. So, directly or indirectly, irrigation is one of the major consumers of groundwater, right? 20% goes towards municipal and industrial. And out of this 60%, that's groundwater, pretty much provided for by the aquifer. There are so many different aquifers in Texas. And out of that, one of the major aquifers is the Ogallala Aquifer, which accounts for about 60% of the total groundwater supply in the state of Texas. And it's one of the biggest aquifers, not only in the state, but also in the country. Okay? Okay. So So what's the major problem we are looking at there? Like I said, a significant portion of these groundwater withdrawals are going towards agriculture, and it's a big agricultural production area and livestock production area. So one of the major issues that they've been seen in the past, that this aquifer levels have declined more severely in certain parts of the state, as well as certain parts of the high plains area, which is kind of the northwest part of the state, because of heavy withdrawals, not because and also because different wells in the state have different pump capacities and different well yields. So it has varied drastically from one county to the other, if you look at it. Now in Texas, it's a pretty interesting state in terms of the water rights, okay? And as, I don't know if many of you have heard about it or not, but in the United States, pretty much water control is dependent on states. Okay? States have the primary control of water, and they definitely have the authority or the capacity to change their water laws as they vary from one state to the other. In Texas, interestingly, the water law is known as the rule of capture. It is also known as the rule of biggest pump. And why is it called that is because basically by definition what it's saying is, as long as you own the land, you can keep on pumping as much water as you want to, as long as there's no detrimental effect on your immediate neighbor or some underlying or some people who are in the nearby vicinity. Okay, so that was about 100 years ago is when the Texas legislature first adopted this law in 1904, and ever since this has been the prevailing law for management of groundwater in the state of Texas. So it's been there's been a lot of modification that's been made in several different parts of the state, but still the law of capture is what prevails there. Okay, it's also known as the law of the biggest pump, like I said. So what's the source of groundwater in Texas? The major source of groundwater, especially in my study area. Okay, so in this study area, the aquifer that pretty much provides for all of the groundwater is known as the Ogallala Aquifer, which is also commonly known as the High Plains Aquifer. So you can see that it pretty much stretches around several different states. It's not just Texas, but starts all the way from South Dakota, Wyoming, Nebraska, Colorado, Kansas, New Mexico, Oklahoma, all the way to mid-Texas. So it's several different states that it's passing. And interestingly, the rules of water management vary from one state to the other. Okay? And in Texas, one of the biggest declines that this aquifer has seen is in Texas, because the rate of recharge has been far less than what has been withdrawn. So in Nebraska, for example, there's not so much of a depletion that you would see as compared to what you would see in the Texas high plains, because it varies from one place to the other. Okay. All right. Now let's look at a little bit background on groundwater management in Texas. In Texas, groundwater is managed through the groundwater conservation districts, which are nothing but local bodies or local political organizations that do have some kind of authority to control water management and also bring out groundwater management plans that are going to be useful for managing groundwater in the state. Okay? And there are so many different groundwater conservation districts in Texas. The area that I was looking at is the High Plains Underground Water Conservation District. They are kind of the oldest groundwater conservation district in Texas. So they prepare a groundwater management plan, which is kind of the basic document that people would follow, while extracting groundwater. But still, rule of capture is always the prevailing law. There's been so many modifications, but ever since it gets into a court ruling or things like that, the most recent rulings have always accepted the rule of water as the prevailing law over other modifications that's been made. Okay, a new implementation that they have seen in the past several years are known as the desired future conditions, which is kind of the big push in several of these groundwater management plans in the groundwater conservation districts. And basically what these desired future conditions are nothing but the quantified condition of groundwater resources at some time in the future. Okay? So what they're really trying to do there is they're trying to quantify some future desired condition in their groundwater management plan. For example, there's a water conservation district pretty close to the High Plains Water Conservation District, which is known as North Plain, and that is where the big beef industry lies in Texas, the Hereford area. I'm sure you all have probably sometime heard about it, the big beef production area in Texas, Hereford, and it's pretty much the North Plains of the state. So there they have enacted a recent desired future condition. It's not very recent, it's about 9 or 10 years now, that said that they have to maintain a 50-50 saturated thickness rule, which is basically saying that in the next 50 years, you want to make sure that the aquifer does have at least 50% of what their current water storage volume is. So they're trying to, like just keep some targets that way, and the groundwater management districts are working with producers to make sure that somehow that is accomplished. So they're trying to put some water use restrictions in those places. Metering of well has been made mandatory and things like that. But there's always so many things that come in when you enforce a policy like that in a state where water has been always governed by water capture. So there's a lot of things that go into it. All right. But that is kind of the major force that is driving all these policy decisions, and even these studies and the funding for studies like this. It's kind of the big push to help policy decisions incorporate these plans. All right. So what is some of the background for including future climate projections in these economic studies? So the background for this is coming from the International Panel on Climate Change Assessment Report 4th, which came out in 2007. And this was a really comparatively well established report, I would say. Yes, sir.
Ask a question about that last line. I'm sorry, but
sure.
But the rule that you specify there, 50 and 50, that's not even sustainable, is it?
That's exactly right. That's not even sustainable, but they have tried to they have not tried to make it an abrupt change in their groundwater management practices. They're trying to make it like more of a smoother transition, like reducing groundwater usage every year by 1%.
So if they didn't have a rule there, and what are they doing now? Are they using more water than? I mean, is the drawdown that quick in the aquifer?
In the North Plains.
Yeah.
In the North Plains, the drawdown has started to see a little bit of impact there actually with this policy. They've started metering the well, so there's a little bit of restriction in what they're using. So they're trying to reach their target.
That doesn't seem to me to be a viable target. I mean, it seems to me that you're withdrawing too much water there, and in 50 years, you've got 50 left, you stop that again, you're not going to have any at all.
But if they do not enact a policy like that, they're going to probably run out of water in the next 10 years, maybe.
Well, that's what I'm asking is the water drawdown faster than that plan, or did they adopt a plan that met the water drawdown today so that they could adopt one?
Yes, that's correct. The drawdown is definitely faster than this projected limit that they have established. And this varies from one county to the other. It's not a generic plan for the whole water conservation district. Like let's say if you move from one county to the other, and that particular county had 180 feet, so probably their drawdown is going to be different than somebody who has 100 feet or 120 feet. So it's definitely based on water drawdown for that current area. Yes. But the study area that I'm going to talk about does not have this desired future condition implemented yet. I was talking about the North Plains. The one that I'm going to talk about does not have this plan implemented yet, and it has not been approved for yet in that area. So, okay. So I was talking about climate projections for this area, and basically I was saying that the whole emphasis or the strength that's coming for this study is coming from the International Panel on Climate Change Projections that came out in 2007 with the IPCC. And what they said is they pretty much conducted the study on several different important agricultural production areas in the country, and they found that while the most productive areas in the country may not change much, but the impact on marginal production areas like the Texas High Plains will be very variable. Okay, so that's kind of a big push for incorporating some climate change related emphasis into research for policy in this area. Now, the Texas High Plains is driven by irrigated agriculture. The Ogallala Aquifer, about annual average about 19 billion gallons of water is being pumped annually. And since 1950, there's a 9% decrease in the overall aquifer storage volume. And this is an average number. Like I said, it would vary drastically as you move from one county to the other or one state to the other. But this is an average number. So So these are some of the projected temperature projections and precipitation projections that they came out with in the year 2009 with the United States Global Climate Research Program. And they pretty much ran two different scenarios. One was the higher emission scenario, and the second was the lower emission scenario. And I'll talk about these emission scenarios in just a little bit here, a little bit more detail. But basically what you can think is higher emission scenarios are future scenarios where you assume that a lot of these future conditions will be driven by fossil fuels. So a lot of carbon emissions will be because of the fossil fuels consumption. And then the lower emission scenario is a little bit more balanced, trying to incorporate some renewable energy, less of fossil fuels. So what they projected is that by the year 2050, there's a temperature increase of about 6 degrees, and by the year 2090, about 13 degrees increase from the baseline of year 2000 would increase. So that's a pretty high, significant projection in terms of temperature increase. And then obviously for the precipitation, as you would expect, since the temperatures are going up, there's not a lot of precipitation that's coming in that area. The lower scenario said about a decline of 20% by 2090, and the higher scenario said a decline of about 40% by 2090 from the baseline of year 2000. So overall, the climate is going to become hotter and drier. Okay. Now, these are some of the changes in groundwater levels or saturated thickness levels in the Ogallala Aquifer from 1950 to 2005. And this is kind of the study area that we are looking at, and you can see that the decline is more than 100 to 150 feet in some areas, and these little, I don't know if you can see that, but those red shaded regions are more than 150 feet of water that has gone down ever since 1950, 2005, in the last 50, 60 years. Okay, so there's been a lot of decline in the state of Texas, which is kind of the big production area, as you would expect. So the specific problem statement for the study is the western side of the Texas High Plains, which is the southern High Plains, and southwest side of the Texas High Plains, and average annual precipitation fell as low as 15 inches from 1971 to 2000 in the last 30 years. Agricultural system with diverse crops is kind of a big characteristic feature of this area. There's a lot of diverse crops. There's a lot of row crops. You have a lot of corn. It's a big cotton producing area as well. It's a big cotton belt in that area. They definitely have some winter wheat and sorghum also for fodder production. So there was a need for an economic analysis to project changes in the regional crop production and profitability, incorporating climate change projections in them. Because previous to this study, I myself did some studies with some of the people who are working in the policy issues, but we had not incorporated future climate projections in our studies so far. We had done a lot of studies on how water management policies could benefit the area, for example, putting a restriction or probably using a biotechnology incorporation into the production system, or probably using multi-year water use restrictions or water allocations, all those kinds of policies. But we hadn't used a lot of climate change projections so far. So I think that was kind of a major motivation for this study. So we had two clearly defined objectives. The first objective was to develop crop production functions by utilizing 4 climate models under 2 emission scenarios for Hale County. It was a county-specific study in the southern high plains of Texas. The second objective was to estimate county-level changes in farm income, crop mix, associated water use by the aquifer, and this was done by incorporating the production functions that you derive by using the climatic projections for temperature and precipitation, and using them as inputs to the economic models, which will drive the profitability of those models. Okay. And then we simulated these results for 3 different time frames. One was the near future, the second was the mid future, and the third was the far future, about 40 years of projection, 2010 to 39, 2040 to 69, and 2070 to 99. So it's a century time frame that we looked at. Okay. The study area is specifically located right here. It's Hale County, and as you can see, pretty much all of this area is completely provided for by the Ogallala Aquifer. This shaded area is, it overlies the Ogallala Aquifer, so all of the groundwater is coming from the aquifer. Weather station that we use for generating climatic projections are, there's a station called Plainview there. We use that. And then total acreages of that, 70% are irrigated and 30% are dryland. And out of the irrigated acres, about 60% is cotton. So that's a big cotton producing area. Most of the irrigation technology in that area, if you've ever flown into Lubbock or the western part of the southern Texas High Plains, if you ever flow into that, you would see a lot of those center pivots that you can easily, like see when you look down the plane. You can see those. That's all you can see there, like those center pivot markings when you travel there. But it's a pretty strong sprinkler irrigation area. There's some drip coming up, but not a lot. This is kind of the major significant production irrigation technology. Economy is about 138 industries, generates an employment about 19,000 jobs per year. So it's a good area to do this study. Now, choice of climate scenarios. I don't want to go too deep into that, but just wanted to give you all an overview for the essence of time. We chose 2 specific climate scenarios, and these climate scenarios are coming from the special report on emission scenario, which was also a part of the International Panel on Climate Change push from the year 2000. So what they did is they came out with 6 different families of emission scenarios, and these emission scenarios are nothing but future projections of how climate will look like in the future based on demographic changes, based on socio-economic changes, based on fossil fuel consumption, people becoming aware. There's a lot of things they put into those scenarios. Okay? So out of that family of 6 scenarios, we chose the A1FI and the A1B scenarios, which are basically FI stands for fossil fuel intensive, and A1B stands for a balanced emphasis on energy sources. So a little bit lower than the higher emission scenarios. So these were kind of the big scenarios that we chose. Then we chose 4 climate models, which are CCSM and the PCM. Both are developed by the NCAR, National Center for Atmospheric Research. We also chose a UK Met Office model, which is the Hadley model. And then we finally chose a GFDL model, which is one developed by the National Center for Atmospheric Research. It's a NOAA model, National Oceanic Administration. Once we got these climate models selected, and these selections were based on certain criteria. First of all, we made sure that there were several previous studies that have been done, even if not on the agriculture side, but at least on some other projections in this area for literature. We made sure that we had these models used before. Second reason was that we had to make sure that all of these models should have had archived daily temperature and precipitation projections for the periods of study, at least from a baseline period. And these were the only models that did have those archived temperature and precipitation projections. So that was one major reason to select these models. Once these models were selected, we applied these climate scenarios to these models, and we found, we then downscaled them because these are global climate models. They're on the bigger, more expanded grid, and we have to downscale them once you reach to a regional study. So downscaling can be done in several different ways, and the process that we use is a simple statistical regression in which you use some local climate projections from a weather station and simply create a regression equation with these projections versus the actual observations and then project them into the future. So it's kind of a simple asynchronous statistical regression. Okay, that's what we use. And these are definitely based on long-term daily observations from Plainview, Texas, which is the weather station. And we had daily temperature and precipitation projections from 1960 to 2009, 30 years of daily data. So that's what we use for our climate data. After that, once we had applied these climate models, the scenarios to the climate models, and then we simulated results over 3 different time frames. So we had 24 sets of climate projections, 4 climate models, 2 different scenarios, and 3 different time frames. So overall 24 sets of climate projections is what we had to compare. These climate projections were then incorporated into crop model, which is known as the DSAT, which is a widely used crop model in this kinds of studies, and I think it's one of the most easily available, I would say, and one of the most dynamic models. You can use a lot of different crop models for different crops, but we just wanted to be consistent with the kind of assumptions we put into for different crops. So we used DSAT for this, the most latest version. And using DSAT, we created yield response functions for 4 different crops in the area, which is cotton, corn, sorghum, and wheat. And these yield response functions were basically a function of applied irrigation water. So we wanted to make sure that these yield responses are definitely a function of applied irrigation water, because all of the water is being pumped from the aquifer. And that's why it's a direct function of the saturated thickness of water withdrawals from the aquifers. Then we incorporated these production functions, which are basically just quadratic response functions, into economic optimization models for using a dynamic model with software called GAMS, okay, General Algebraic Modeling System. So a typical objective function looks like this. Okay, I'm sure some of you have probably seen it before. It's nothing but a maximization function, okay, that you do in linear programming. And you are maximizing the net present value of net returns over a simulated time frame. So we did it for every 30 years of time frames that we chose, for the near future, mid future, and the far future. Now the net revenue was defined as a function of the money that we made out of those crops. Okay. Now the PI stands for price of those crops. Y is the production function, so price times what you're getting. And the production function is a function of water applied and water pumped. Okay, so basically you're getting net returns here, and then you're subtracting the costs of production, which are a function of water pumped, saturated thickness, and the pump lift. So those are kind of the formula that we looked at. Basically, we are looking at just net returns here. Okay. We also had to put in some constraints to the model, or else it would give some really erratic results. But we just did not want to constrain it too much, with the policy side of it. We just wanted to keep it as open as we could. Okay. So the first constraint we definitely wanted to put there, which is kind of a generic constraint there when you do nonlinear programming like that, you definitely have some constraints like you want to make sure that all of your water applied in that county is equal to the water that is being pumped on different crops. Okay. So you want to make sure that equals each other. The total water should have to be less than the gross pumping capacity. You cannot exceed that. All of the irrigated, fractional sum of irrigated acreages versus dryland acreages should equal 100%. Okay? And then we don't want to put any water on dryland crops, and we don't have any dryland corn acreages in that area. These were kind of the constraints that we put on there. Okay. The data input to the model consisted of hydrological parameters like saturated thickness, recharge, well yield, which are pretty much just geological parameters that we got from the USGS, and also Texas Tech University's Geospatial Center, who do a lot of work on estimating these parameters from one year to the other for the aquifer. We also took acreages, input prices and output prices from the FSA, acreages coming from FSA, 5-year average, input and output prices from the crop budgets at Texas Agri-Life Extension, that was also an average figure, and definitely the irrigated functions and the dryland yields are coming from the crop models. So before we put this information into the crop models, I just wanted to show you all how the climate projections looked before we started crop modeling. So as you can see, the white bars here is basically the observed or the baseline figure, and the 4 colors are the 4 models: GFDL, Hadley model, PCM, and the CCSM model. So towards the end of the century, if you look, the PCM and the CCSM model were the ones that predicted the least increase in temperature, okay, for both the scenarios, low as well as the high scenario. Low is the A1B scenario, and high is the A1FI, or the fossil fuel intensive scenario. So PCM and the CCSM both indicated lower declines, lower increases in temperatures, Now what about precipitation? Towards the end of the century, the PCM and the CCSM model showed the highest increases in precipitation. So basically both the CCSM and the PCM model said that temperatures won't go that high, but probably precipitations will go pretty high as compared to the other models. Okay. All right. And these were the CO2 levels. Now the good thing, and if any of you are ever interested in working with crop models, DSAT is a very flexible model that way. It allows for CO2 fertilization effects, which not several of the models will allow. So this allows you to change the CO2 levels, which is one of the major assumptions of the scenarios in the first place, right? Basically, you are looking at different CO2 levels in your crop models, in your scenarios in the future. So we varied the carbon CO2 levels in each of these scenarios whenever we input production parameters and other parameters, climatic parameters, into DSAT. And definitely, as you can see, CO2 levels increased from 346 to as high as 838 towards the end of the century. Okay. So what were some of the results? The results for the dryland yields were pretty interesting. Okay. Now, The PCM and the CCSM model, which did say that there were higher precipitation chances and there were lower increases in temperature predicted by them, we definitely saw an increase in cotton yields amongst all the 4 models towards the end of the century. Sorghum yields also saw increases. Highest increases were recorded for CCSM, which is kind of the model from which did predict high precipitation increase. GFDL is the only model that said that sorghum yields may decline, and I'm not really sure why that happened, although we were expecting an increase on that as well. And then also for the wheat, we did see increase in yields over the next 100 years for all the 4 models. But the highest increases in dryland yields were predicted by the CCSM and the PCM model. Okay. Now these are the results for climate predictions under the mid-range scenario. Okay. There are 4 major parameters which I think would interest all of us as an audience. So the first was average saturated thickness. And average saturated thickness did not really show a lot of difference among the 4 models, but because that is basically governed by the amount of water being pumped in an unrestricted scenario. We have not put any constraint there in terms of the water management plans or the 50-50 constraint or anything like that. We are just thinking that people are going to operate the way they are. There's really no policy issue coming in, because this was not modeled on a policy basis. This was just modeled on a general behavior of the irrigators or producers in that area. So definitely the average saturated thickness fell from 80 to 30 feet, after which there's hardly any possibility of getting any water from those wells, or it becomes extremely unprofitable, or it's not economical to pump any more water. That was the same case for all the 4 models and scenario. All the 4 models under the A1B scenario. Total water used per cropland acre definitely also decreased because there was no water available. Irrigated acres as a percent of acres starting at 72% went as low as 2% towards the end of the scenario, end of the century. Here it pretty much went to dryland. Here went to about 1.6. So almost went to dryland towards the end of the century for all of the 4 models. The only big difference that you would expect is in the average net income per acre, and that's only because there was difference in the dryland yields in that area as impacted by precipitation and temperature. Okay, so one of the biggest increases in dryland yields was for the CCSM. However, in the A1B scenario, we did not see a lot of overall net revenue increase. However, the GFDL showed increase, and the PCM model definitely showed one of the highest increases in overall net revenue towards the end of the century. Very similar results for the higher emission scenario as well. Saturated thickness declined same way. Water use per cropland acre definitely declined. Irrigated acres went to dryland. Net income is the only one that saw changes, and here CCSM model, which was the higher emissions model, higher emission scenario had the highest increase in average net revenue, and definitely PCM showed an increase. Okay, and Hadley model showed a decrease. So one of the major conclusions of this study are dryland yields of cotton, wheat, sorghum definitely positively respond to the elevated levels of carbon dioxide in the future. There were definitely higher yields in the higher emission scenarios compared to the balanced. So basically when there's more CO2 in the atmosphere, at least with the DSAT predictions, it does say that increase in dryland yields will occur. A1B scenario, CCSM and Hadley showed decline. GFDL and PCM showed increase. In the A1FI or the higher emission scenario, all the 3 models showed increase except for the Hadley model. Now, as is the case with several studies, there's also some limitations which I definitely wanted to bring to your notice. First off, these models are county average models. Okay, so we assume county average hydrological data. That's the best we could get. So it's just taking an average saturated thickness in the entire county, while the real case is that it might vary from one well to the other. Okay. That's one of the major constraints to the model. Also, we assumed irrigation technology being constant, which is also one of the major limitations, and definitely that is something which we can expect to be becoming more efficient in the future in some way or the other. So we did not have any way to model it. And then one of the recent study by Tewari and Bruce McCall, he's a big climate research person at Texas A&M. So they came out with a study in 2011, and they say that most crop models, including DSAT, overestimate the effect of CO2 fertilization effects. So that is also something which is kind of inherently built into the model that I think probably led to those extremely high yields in some cases. So the big takeaways from this study. Climatic predictions for the Texas High Plains is definitely going to become warmer, drier, precipitation is going to go down. Okay, there's a stress on groundwater resources which is definitely going to go up. So policy management or policy intervention becomes crucial, and that is why there is a need for including at least some of these assumptions into the groundwater management plans. Okay, and some of the future research efforts would be to do this analysis on a more regional scale than just a county basis. So that would be some of the future efforts that we would like to do this study on, and also probably do it on international scale if possible. The only major limitations to study like this comes with the fact that there's not availability of continuous daily time series data for precipitation, temperature in several of those areas. So that's kind of the big takeaway from here. Any questions on this? I would be happy to answer them, and that's all I have to. Yes, sir.
So you had 3 periods out into the future, and you discounted the economic activity from 2099 to current day. Is that what? Because you were looking at net present value.
Yes.
So basically, that period is 0. Because there's no discount rate that you could use and not have that value at 0, right?
That's correct. Yes.
And probably the middle one is valued close to 0, if not 0.
That's correct, because that's kind of the most recent we could go towards. Yes.
So the impact of the increased yields or anything else of this thing is really focused on the first third of the thing.
Yes.
And those impacts may or may not occur during the first third. They may be occurring later, right?
That's correct. That's correct as well. That's correct as well. And that is why I was saying there were some limitations on this study as to how we could change the discount rate for individual time periods, because we were just using the same model, and we did not vary discount. Well,
you shouldn't. You didn't have to go out that far. You know, that's an artifact of what the scientists want to look at, but in economics, that stuff really doesn't matter if you're going to discount it.
That's true. And discount rate is always a big question in studies like this, and I've seen that before as well. And because there's always people even argue about it, but how do you want to vary discount rate from one year to the other? But I don't know how to rightly put it into the model that way. That whenever we were doing this study, but you have a valid point there. We are looking really at the next 30 years, where actually very little that we can do during that time. That's correct. That's correct. Yes. But that's something definitely we want to look at, as how to incorporate that yearly change of discount rate would be a good idea to look at. Yes.
I think the only way you could do that is by breaking it up into 3 separate models, looking at the net present value during those 3 time periods.
Right.
And then trying to merge those together.
Yes, I think so too. Yes, it will definitely have to be a separate model. Yes.
So if you look broadly beyond just Texas and the scope of your study, and you think broader in terms of water use and climate change in the West, what are the implications of this work and the broader view on Tennessee agriculture?
I would say Tennessee agriculture is not all that driven by groundwater. Currently, as to what my best knowledge is so far, I've not worked very closely here, but I know that there's a lot of reliance on surface water and natural precipitation here. But definitely, in the near future, or maybe not so far off in the future, this may become one of the major issues, because I know that in West Tennessee, there are certain irrigators in the area who are starting to look at a risk management approach for getting sprinkler irrigation in and relying on wells like that. So definitely a study like this would be at least able to give you some idea, what's going to happen in the future. Although this is not 100%, we cannot really predict for this area, but groundwater resources are one of the major focus of this study. So we can probably modulate it for surface water somehow and try to see what happens.
I was thinking more from the perspective of the water use and temperature changes in the West. Does that provide opportunities for us here? And then you take that a step farther, does that impact any kind of faculty that we
research-wise.
Definitely the major crops, I mean, Aaron can back me up on that. I mean, corn, soybean, and wheat are really not depending on groundwater.
No, and we have substantially different underground aquifer systems in Tennessee.
In Tennessee, then.
Our recharge rates are so that we're not in a deficit scenario in most cases when we're irrigating between the two rivers, right?
And the major issues with groundwater, you're going to find it, for example, in crops. For example, tomatoes in Rainier County. Talk with any producer there, they're going to tell you one of the major issues they have is water and groundwater major. So when you think on the broader side of the economic impact, probably we don't see it in the short run because major crops are not going through that. But we still see minor things, and one that comes to my mind is Rainier County. Yeah.
And that's really caused by all the wells drilled, drawing water at the same time, creating a cone of no water that gets refilled during the winter.
That's correct.
And you know, based on what I heard, I guess it was about 6 months ago. The groundwater, if you look at the recharge rate versus our use, we're very far from what do I want to say? We've got plenty of water in the ground table. Yeah. It's how deep do you have to drill the well?
Right.
Exactly.
And the location of the well.
So the energy that you need to take that water out of the ground.
The pump lift will be very different for a county like in Tennessee versus what's in California, or and then the water laws in the state will make a difference. That makes a lot of difference as to how much state regulation can go into. Like New Mexico versus Texas is very different. So yeah. Any other questions?
Can I ask how you define the dry thing? Because I noticed that in our result there is a conclusion that much of the area becoming more and more dry.
Yes.
But because I know that you define this by the acreage that is less and less irrigated.
The dragon acreage is 100% non-irrigated. There's no wells of that county, because in Texas at least the FSA does maintain those exact, like survey of acres of how much irrigated really, how many wells are catering towards irrigated acres, how many completely dry land, how many drip. So we do have that exact, data there.
But you also mentioned that if we predict the temperature, the precipitation will also be greater. So would that be possible that since we have a more rainfall, but those irrigated land is coming less, so would it be possible that those dry areas will also be irrigated by the rainfall?
Yeah, that is exactly why those dry land yields went high in those future time frames. That is the reason why those dry land yields went high, and that's why the crop mix shifted from irrigated towards dry land towards the end of the century. Yeah, that's correct. Yes, good point.
Does it shift the timing of the precipitation in addition to the quantity across states? Because a lot of the times the biggest issue isn't the total amount of rainfall, it's when the rainfall occurs as to whether you'll make a crop or not.
Yes. So DSAT allows for adjusting that by using adjusting for irrigated demand on a seasonal basis. It allows you to do that. Like you can calculate the average seasonal irrigation demand from one season to the other on a daily basis. You can actually incorporate that into that by subtracting from the overall evapotranspiration your precipitation. So it can give.
But on the dry land, you could have a set of circumstances where you get massive precipitation deficits at key growing times of the year, which would probably substantially change what your yield estimation is.
Yes, that's quite a possibility, because all these climatic projections are also downscaled on the basis of historical projections. That's a big limitation in studies like that. Yes, I agree. Yes, that's true.
Any other questions? If not, this